Okay, so hi everybody. Thanks for listening in. In this recording, what I want to do is talk a little bit more about one of the more counterintuitive aspects of quantum physics, which are the uncertainty principles. These are statements that certain parameters cannot be measured simultaneously. The most famous of these, which shows up in various cartoons, etc., is the one that involves position and momentum, which is basically velocity. It says that the uncertainty in the position of an object times the uncertainty in the momentum of the object, here designated as delta x and delta p respectively, that product needs to be greater than Planck's constant divided by 4 pi. That basically nothing you can do can allow you to make this product smaller than that number. What that means is that if we know the position of the object extremely well, then there needs to be a large uncertainty in its momentum. Similarly, if there's a large uncertainty in the position, the momentum can be measured very well. Or if the momentum is known very well, the position cannot be known well. Now, this violates our intuition badly. If you look at the motion of anything in classical mechanics, you can imagine I'm looking at how its position changes over time and how its velocity changes over time. And I can measure both of those arbitrarily well. This says that at fine enough scales, that's not the case. And what I want to try and explain is why this happens. Give you a sense so that it doesn't just seem like a weird statement that comes out of the blue. And the reason this equation emerges is because at the quantum level, we're no longer talking about discrete particles moving through space. We have to use this thing called the wave function to describe the interactions and motions and distribution of objects. Now, just to remind you, a wave function is a function of space. It's basically something you can draw that gives you something related to the probability of the particle being at a given location. So fundamentally, a wave function is a function of all 3 coordinates. But in practice, what we tend to do is plot just a line as a function of 1 coordinate, just to be simple. So this is giving us the wave, a couple of different wave functions for particles as a function of basically the x coordinate. In this case, the function is pretty much 0, except it has a peak here, goes a little negative and comes back. In this case, the wave function is a sinusoid. Both of these are allowed configurations. There are actually fairly loose constraints on what the shape of the wave function has to be, especially if we don't have other interacting forces. Both of these are pretty allowed wave functions. But all of quantum physics says these are the real things. You don't have a particle moving through space. You have instead wave functions evolving over time. And the wave function tells you what's the probability that a particle will be detected at a given location. And since these functions can be positive and negative and actually more complicated than that, in practice, it's something related to the square of these functions, something that's positive. The trick is, depending on what type of wave function you can either have something that tells you the position very well or the momentum very well, but it can't do both. And I want to try and explain why that is. So let's first consider the case of a sinusoidal wave function. Sinusoidal wave functions are actually really good at giving information about the momentum because they evolve in a very specific way. Basically, a wave function that's a pure sinusoid keeps its shape, but its crests and troughs move through space in a very predictable, regular way. The shape of this function never really changes, it just propagates. That's really good because it means that the shape of this wave function changes regularly with time. This means it has a very well-defined momentum. And that well-defined momentum being tied to the structure of this wave function is actually what allowed these interference experiments that we talked about in the previous recording to work. In these cases, you prepare electrons with a well-defined momentum, basically a well-defined velocity, that corresponds to a wave function that's very close to a sinusoidal plane wave. That plane wave turned out to have a wavelength that is set by the momentum. It's given by this equation down here, where lambda is h over p. This is often called the de Broglie wavelength. That since that wave gets everywhere, it allowed it to interfere and produce this interference pattern. But that also reveals an aspect of this particular type of wave function that is important to understand. Since this is a plane wave and there's basically probability everywhere, the particle could be here, could be found here, 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 here. It can be found basically anywhere. The position of this particle is extremely poorly determined. So if you create a state that has a well-defined wavelength, a well-defined momentum, you don't have a very good idea of where it's located. Now, and that's just the way that type of wave function works. Now, you can consider the other type of wave function. You could create a wave function that looks like this. It's got a very sharp peak. The particle, there's only one place where the probability of finding the particle is high, right here. Everywhere else, it's basically 0. If that's the wave function, then you know where the particle is going to be at this time. The trick to remember is this is the wave function at one time. If you want to know how the particle moves or what its momentum is, you need to know something about how this evolves over time. And the thing is, this particular wave function doesn't stay looking like this. If you start the wave function like this and just don't confine it in any way, this sort of wave function will naturally spread out. Just like if you create a region of high electric fields in one location, it tends to distort and go away. But think about this. You start with something that has a high probability of being in one place, but then it spreads out. That means that the particle has a finite probability of moving different distances. This implicitly means it has a poorly defined velocity, a poorly defined momentum. Its momentum could be nearly anything given how fast it spreads. There are some limits on that. But it turns out the way these wave functions evolve over time is in such a way that makes it very hard to constrain their momentum. In fact, you can't do it. So you can either have wave functions that have very well-defined momentum, in which case the position is not determined, or you have wave functions that define the position at one time very well, but then don't define how that thing evolves very well. Or let's be clear about this. How this evolves over time is mathematically determined. It is very well established. But since this is only the probability that the particle is at a location, the fact that it spreads means you can't predict exactly where this particle is going to be in the future very well. It could be exactly where it started, 0 velocity, 0 momentum. It could have moved to the right. It could have moved to the left. And the rate at which it does that is basically set by how narrow you made it to start with. So the math behind quantum wave functions basically allows you to create things that are well localized in position or have well-defined momenta, but not both. Now, one thing I do want to mention is that, remember, this uncertainty relationship applies to simultaneous measurements. It is possible to make a measurement of the position that is very accurate after you make a measurement of its momentum. This kind of experiment with the interference patterns with electrons is an example of that. When the particles are launched and when they pass through these slits, they have a well-defined momentum. And so the wave function is set by a very oscillatory sinusoidal function. But when those things are detected, they are detected as individual particles. So at that point, the wave function is spatially localized. Suddenly it's localized at one location, which depends on how the wave propagated before that. One of the areas of quantum physics, fundamental quantum physics, that is still an active area of research is how that transition happened. Something happened when the electron was detected that transformed its wave function from a plane wave to one of these localized functions. Now, that probably involved the interaction between this wave function and all of the things that are in the detector. But it's not like there was a one-to-one correspondence there, because you can prepare the electron in almost the same state, and it could end up here or here or here or here. Understanding how that probability actually works is still a place where people debate and discuss. And so I'm not going to get too far into it here. But this is where questions about what this wave function actually is get interesting, but is also something I can't expect you guys to actually know, because nobody actually knows that yet. Now, again, in practice, this uncertainty principle only really kicks in for subatomic particles on the atomic scale. The reason we don't experience this in our day-to-day lives is because this Planck's constant is very small. And you have a couple of problems to get a sense of when it's going to be relevant. Here's just one, for example. Say we could measure the position of a single proton to within a micron, which is, on the size scales of humans, pretty small. So 10 to the minus 6 meters. What is the smallest possible uncertainty in its speed? Okay, we can answer that using this equation. The uncertainty in the speed is just the uncertainty in the momentum divided by the mass. Well, that's not too hard to calculate. The uncertainty in the momentum is going to be greater than h over 4 pi delta x. So we can just stick that in here. And these are all numbers we know. H is a fundamental constant, 6.6 times 10 to the minus 34 kilograms meter squared per second. The mass of a proton is well known, 1.7 times 10 to the minus 27 kilograms. And the uncertainty in the position is given, 10 to the minus 6 meters. What this works out to, apologies for the seconds there, is when you plug in all those numbers, 0.03 meters per second. So the uncertainty in the motion of it corresponds to 3 centimeters per second, which is pretty small. It doesn't take much to perturb a proton by that amount. So hopefully that makes sense, that this is a small uncertainty, practically speaking. However, if we go to even smaller scales, say to an atom, then this starts to become important. 10 to the minus 10 meters is what? If we stick in that, now we're getting uncertainties in the speed of order 300 meters per second. That starts to sound significant. And if we instead consider it an electron, which has an even lower mass, then this uncertainty starts to become large. What this means is that we can't neglect the quantum nature of these objects, the fact they have wave functions, when we work at the atomic scale. And all of our data is consistent with that. These sorts of uncertainty relationships are very relevant for understanding the physics of individual atoms. Now, while the position momentum uncertainty is the one that is most famous, there is another one I do want to mention. This is one that involves the uncertainty in energy and the uncertainty in time. And it's the same basic form. Delta E, the uncertainty in energy, and delta T, the uncertainty in time, is got to be greater than h over 4 pi. This relationship, to a lot of people, is even weirder than the previous relationship, because energy is understood as a property of systems that is the thing that can't change. And time is a coordinate. It's when something happened. Why are these in any way related to each other? It seems to suggest also that energy conservation isn't perfect in quantum mechanics. And indeed, one way this equation is often interpreted is that you can violate conservation of energy if you do it fast enough. And that's actually kind of true. But rather than just state this generically, I want to give you an example which I think makes these uncertainty in energy and uncertainty in time more clear. Like, uncertainty in position makes sense. Uncertainty in momentum makes sense. What does uncertainty in time mean? Well, the cleanest demonstration, I think, of this uncertainty relationship involves the interaction between light and atoms, which we'll talk about a lot in the next recording. The idea is basically this. With certain atoms, if you shine a light of a specific wavelength on them, those atoms can change state, becoming a different quantum mechanical thing for a short period of time before they return back to their original state and release that light. This is the basis between why light of certain colors scatters with certain atoms. Again, this is just a process where two things interact to produce one combined thing and then turn back into their component parts. Now, the way this is understood quantum mechanically is that this combined thing is a different quantum mechanical state. It's called an excited state, which has a different wave function than the initial state. The question is, what wavelengths of light can do this? And it turns out that the range of wavelengths of light that can do this depend on how long this excited state can last. If you have this configuration can last for a long period of time, turns out only very restricted wavelengths can do that. Only one color of light can do it, maybe 455 nanometers. Only that allows this interaction to happen. If this excited state lasts for a shorter period of time, a broader range of wavelengths can produce this effect. And this is something you can measure. You can measure how long these excited states last by sending in brief pulses of light and seeing how quickly the light comes out again. And you can also measure what different wavelengths of light allow this transition to happen. Those are different experiments, but you can make them. And it does turn out that if you want a broader range of wavelengths to produce this effect, you need the lifetime of this state to be a shorter number. Now, what's interesting is it turns out mathematically, there's no difference in the states that you get depending on the wavelength here, which is, again, somewhat counterintuitive. You might think, okay, if I send in something with a slightly different wavelength, it produces a slightly different excited state. That's actually not the case. They all produce the exact same excited state, which is where the potential violation of energy arises. Remember, light of different wavelengths has different energies. So this initial state, if you have different wavelengths of light, have different energies. When they form this state, they all are the same state. They should all have the same energy and then turn into different energies again. The only way to reconcile this is to say that this state's energy is not completely well determined. It has some uncertainty, which is set by how long that state can exist for. If you have a state that can exist for a short period of time, it can accommodate a range of energies coming in or going out. If you have a long-lived state, it can accommodate only a narrow range of incident energies. And just to say, the light coming in and the light going out has to have the same wavelength because this is a long period of time. This, I think, makes a little more sense out of this relationship. Delta T isn't like the uncertainty in when one event happened. It's more the lifetime of this combined state, this excited state. And the uncertainty is energy is the difference in energy between these two things and whatever this is, which only lasts for a finite time. And again, this uncertainty in energy is usually fairly small. For example, if you have some atomic state that lasts for only a microsecond, 10 to the minus 6 seconds, then this energy uncertainty turns out to be like 5 times 10 to the minus 29 joules, which is a very small energy. That is the kinetic energy of an electron moving at only 10 meters every second. But this is important because this does creep into various processes in quantum mechanical systems. This is part of how we understand, say, certain types of electron microscopes working. This is part of how nuclear decay works. It allows for transitions to happen between states that if you did everything perfectly, where energy conservation had to be true at all cases, wouldn't happen. And the specific, again, conditions you'll consider in your assignments are things where this is not just an atom changing states. This involves actual changes in the properties of subatomic particles. For example, if you throw electrons and protons into each other, they can form neutrons. They can form different particles that have different charges that then decay, and it exhibits this exact same behavior. So again, the goal here is just to give you some sense of where these equations come from and how they can be used. We'll now look at a few more practical examples in the next recording of what these transitions actually tell us about these particular states that subatomic particles are in. Thank you very much for your time and attention.